let's say that I have the power supply here. I have a switch that's closed, capacitor, and inductor. So I basically turn this thing on. It's going to start out, not a lot of back current going this way to start out with, but over time, this is going to charge up. When this is charged, we disconnect it perfectly. Again, no sparking. Do it fast enough. We have the magic to do it. So now I have a charge capacitor and an inductor. Some capacitance C. Kirchhoff's rule still applies. So let's see, that was the positive side. So that's the positive, negative side, the positive and negative side. I have all these electrons on this side, which are now going to start moving in that direction, and they're going to come around to this side. So my current is flowing in that direction. So I'm going to start here, work my way around. So I have the voltage across the capacitor plus the voltage across the inductor equals 0. The voltage across the capacitor, I know that C is equal to Q over delta V. And so delta V is equal to Q over C. So this becomes Q over C minus L times di dt equals 0. Remember that current is dq dt. However, we need to be careful about the Q's, and this is the place where I typically mess up in class, and hopefully, well, you'll get the edited version if I mess up. This is the charge going through the inductor. That is the charge on the capacitor. They are not the same. Matter of fact, the change in this Q and the change in this Q are negatives of each other. This, as their charge leaves here, so as there's a delta Q here, there is a delta Q here. So if that's negative, this is positive because these are the charges coming from that. It depends on which one I want to do here. So this is Q over C minus L times negative d big Q dt equal up second derivative, because I is dq dt, and we're taking the derivative again, equals 0. So I have Q over C plus L second derivative of Q with respect to time. Now we can solve for Q. So Q over C is negative L d squared Q dt. So I need some function whose second derivative will get me basically what I start with, besides some constants. We can put the constants together if we have to. And sine and cosine function work very nicely. So if we start with Q at its maximum, this is the charge on the capacitor, cosine makes more sense. Q sub naught cosine of omega t. So the second derivative of Q with respect to time, and this is the dot notation for second derivative with respect to time. I believe that was what Newton did. Leibniz, slightly different notation. So I take the second derivative, so derivative of cosine is negative sine, derivative of negative sine is negative cosine. So Q double dot is equal to negative Q sub naught omega squared cosine omega t. And so this now becomes Q sub naught over C times the cosine of omega t is equal to negative L times negative Q sub naught omega squared cosine omega t. Technically, you're not canceling, you're comparing coefficients, but good enough for physics. The initial charge on it really doesn't matter. And what we're left with is the two minus signs cancel out. So 1 over LC is equal to omega squared. So the angular frequency is equal to 1 over the square root of LC. But also notice what the implication is here. We can describe the charge on the capacitor with this cosine function, which means it oscillates back and forth. So what's happening in our circuit is that all the charge starts on the positive plate, it's going to all end up over on the negative plate, and then it's going to all float back and then back, and it's going to oscillate back and forth in some sort of harmonic motion. We are assuming there's no resistance in this because it's a pen and paper problem, so we can assume those things.